Flip a switch and instantly your room comes alive. Lights glow, fans spin, screens wake up. But pause for a second, because the electricity powering that moment may have traveled hundreds, even thousands of kilometers before reaching you. It crossed mountains, rivers, cities, and storms, all without a visible container. No pipes, no boxes, just thin metal lines hanging quietly in the air. How does something you can't see move so far, so fast, without fading away? That mystery is exactly what we're unpacking today, as we ask the question, how do power lines carry electricity over long distances? Let's find out together, right here, on History of Simple Things. To understand power lines, we first need to understand what electricity actually is. Electricity isn't a substance flowing like water, it's energy being transferred through moving electric charges, usually electrons. These electrons don't race from the power plant to your home at lightning speed. In fact, they barely move at all. What travels fast is the energy itself, passed along almost instantly through an electric field, like a ripple moving across a pond. This subtle difference matters because it means power lines aren't shipping electrons across countries. They're creating a controlled pathway that allows energy to propagate efficiently from where it's generated to where it's needed. The challenge isn't speed, it's loss. Over long distances, energy has many ways to escape, especially as heat. And this is where power lines become a clever balancing act between physics and engineering. If electricity naturally wants to move, why can't we just send it down any wire we want? The answer is resistance. Every wire resists the flow of electric current, and when current meets resistance, some energy turns into heat. Over short distances, that loss is negligible. Over long distances, it becomes expensive and wasteful. The more current you push through a wire, the more heat it produces. That means if you want to send a lot of power far away using low voltage, you end up wasting huge amounts of energy warming the air. Early electrical systems struggled with this limitation, which is why the first power plants had to be built close to the people they served. The solution that changed everything was not stronger wires, but smarter voltage. Here's the key idea. Power equals voltage times current. If you increase the voltage, you can send the same amount of power using much less current. Less current means far less heat loss in the wires. This simple mathematical relationship is the secret behind long-distance power transmission. Power lines carry electricity at extremely high voltages, often hundreds of thousands of volts. At these levels, the current is low enough that energy loss stays manageable, even across vast distances. This is why transmission towers are tall and spaced far apart. High-voltage electricity needs room and insulation, even when it's just flowing through open air. Without high voltage, modern electrical grids simply wouldn't exist. Cities would need power plants on every block. Instead, we centralize generation and stretch its reach across entire nations. High voltage is great for transmission, but terrible for everyday use. That's where transformers come in. A transformer is a deceptively simple device that changes voltage levels using magnetic fields and coils of wire. No moving parts required. At a power plant, transformers step voltage up to extreme levels before electricity enters long-distance transmission lines. Near cities and neighborhoods, other transformers step it back down in stages until it's safe for homes and appliances. This constant stepping up and down is what allows power lines to be both efficient and practical. Transformers made long-distance electricity not just possible, but economical. They are the silent intermediaries that let energy shift shapes without changing its essence. The dominance of transformers is also why alternating current, or AC, became the global standard. AC naturally changes direction many times per second, which makes it easy to transform voltage levels. Direct current, or DC, doesn't do this naturally, making it historically harder to adapt for long distances. This difference fueled one of the most famous technological battles in history. In the end, AC won because it could travel farther with less loss. Today, most power lines still use AC for that reason. Interestingly, modern technology has brought DC back into the picture for certain ultra-long or underwater connections, but the core principle remains the same: manage voltage carefully, and distance becomes manageable. One of the strangest things about power lines is that they're often uninsulated. This seems dangerous, but air itself is a surprisingly good insulator. As long as the wires are high enough and spaced far apart, electricity stays right where it's supposed to be. Elevation also protects lines from people, animals, and ground moisture, all of which could create unintended paths for electricity. The tall towers and pylons aren't just structural. They're safety devices shaped by physics. In some environments, like cities or underwater routes, power lines are insulated and buried. But overhead lines remain the most efficient and economical choice for long distances, which is why they dominate open landscapes. Even with all these tricks, some energy is always lost. Engineers constantly work to minimize that loss by choosing materials like aluminum and steel, which balance conductivity, strength, and cost. Lines are carefully tensioned to prevent sag, which increases resistance, especially in hot weather. Weather itself becomes part of the system. Wind cools wires, reducing resistance. Heat makes them expand. Ice adds weight. Power grids are designed to handle all of it, adjusting and compensating in real time. What makes this remarkable is not that losses exist, but that they're kept low enough to power entire continents reliably, day and night. Power lines aren't just wires. They're the physical expression of a massive synchronized system. Power plants must generate electricity at precisely the right frequency and phase, so energy flows smoothly across the grid. One imbalance can ripple across regions in seconds. Every time you plug in a device, you're tapping into this invisible choreography. Electricity doesn't know your address, but the grid guides it flawlessly, directing energy exactly where demand appears. What looks like a simple line against the sky is actually one of humanity's most sophisticated machines. Thank you for watching. If you have suggestions for our next video, feel free to share them in the comments below. We'll be sure to give you an acknowledgement for your contribution. Thank you for joining us on this journey through the history of simple things. Don't forget to like, subscribe, and stay tuned for more stories woven through the smallest details.